Hey everybody, we're gonna get started right on the hour today. We got a good amount to cover and some really cool things to talk about. Welcome to today's live event. I'm Greg Paulson from Xometry, and I'm excited for you joining us today. We're going to spend the next hour discussing design best practices for additive manufacturing. Our goal is to give you a practical, actionable advice and to help you optimize your parts, reduce costs, and get the most out of industrial 3D printing technologies. I'm joined by my co-host. I'm not sure which direction I'm pointing, but he's either up, down, left, or right of me right now for you. Senior Solutions Engineer Matt Schmidt for additive manufacturing. He brings a ton of hands-on experience. I'm thrilled to be able to share these design principles with you all today. So let's just talk about the agenda really quick. We're going to start with some brief introductions. We're going to learn a little bit about Xometry and then move into our core 3D printing topic. I want us to first shift our paradigm into an additive manufacturing mindset, thinking about how your design will grow and what that really means. And then we're going to show some examples and go into specific design tips and tricks. I also have some news and some resources that we're going to share at the end, and that's going to be followed by our live Q&A. You, the audience, are participants. You have the opportunity to submit questions at any time using the Q&A tab on the Zoom webinar platform. Matt and I will try to get to as many questions as possible at the tail end of this webinar. Any overflow, submit away. We're going to tackle those after the event. Finally, this is all recorded. We're going to send the email with our blog post link that's hosting the recording. It'll have a summary and some of the questions and answers that we had during this event. That way you can watch it again or share it with your colleagues. So let's just jump right in. First off, again, I'll reintroduce myself. My name is Greg Paulson. I'm Director of Category Management here at Xometry, focusing on additive manufacturing. I've been in the advanced and additive manufacturing industry for 16, 17 plus years, and I have really fallen in love with making parts, understanding materials, design for manufacturing processes, and the different processes and the outcomes of those. Joining me today is Matt Schmidt, our Senior Solutions Engineer. And Matt, do you want to give a quick introduction?
Sure, absolutely. Great to be aboard. Thank you very much. Again, Matt Schmidt. I am the Senior Solutions Engineer for Xometry, focusing on additive manufacturing. I have been involved with new product development and additive manufacturing for quite a while. Don't want to date myself too much, but my primary roles and responsibilities here are to help our customers with the various, design for additive manufacturing, the various print platforms, materials, and processes that go along with making additive parts. Great to be here.
Yeah, absolutely. And thanks for joining us, Matt. And I think what's kind of cool about this, if you look at Matt and my background, we see more than just additive, right? So we also kind of see it at a holistic, like where it works and where we suggest it as a solution. So speaking of that, we work in a multidisciplinary company. We are a digital manufacturing marketplace called Xometry. Founded in late 2013, really started making parts for customers in 2014, and actually went public XMTR under NASDAQ in June 2021. So it's been a very exciting journey. And over the course of our marketplace, we've now are serving over 71,000 active customers, which is super exciting. And what's great is every single time I do a webinar, our quarterly report will come out, and I'll be able to up that number, which is always fantastic. We're a two-sided marketplace, so not only do I work with the buyers, those who need stuff made, we use a digital interface for that. We work with our suppliers, those who can produce those goods on demand. We celebrate the diversity of the manufacturing supply base, both domestic and globally, and we're able to offer solutions across the board from low volume work all the way up to scaled and sustained production. And that's over dozens of manufacturing processes. Our platform marketplace, like I said, is that two-sided buyer and seller. What really knits together is our AI integration. We have a platform, it's called the Xometry Instant Quoting Engine for our customers. It's a single one-stop shop where you can go and upload your technical files, get pricing and lead time right away. We actually use AI to predict and give you real-time costing information on your project. You get to change the settings, configure your quote, pricing and lead time will update. And when you're ready, press buy, and then it'll go to our network. Our network is advanced suppliers. We actually use AI to match make the project scope with those who best complete that work, and we're able to make that match through both our domestic and global needs, depending on what your needs are for your project. So it's a really dynamic system. It kind of gives you that one-click feel that you would have at an e-commerce platform, only it's your custom manufactured parts. But like I said, I wanted to introduce us. I wanted to talk a little bit about Xometry. But there's a lot of meat and potatoes today here, folks. So we're going to be talking about why 3D print and then the design tips for 3D printing. So first off, some of you may not be in the 3D printing world. Some of you may be learning about it right now, or may just need a little refresher course of what additive manufacturing really means. And additive manufacturing is all about growing parts. So on the contrary, when you think about subtractive, like a CNC operation, you're taking a stock material and then you're cutting it down to size. I take a sheet stock, I use a laser to cut it down. I take a end mill or a drill, I reduce material, working to get my final part. With additive manufacturing, a part design, a 3D model, is interpreted in build software, often called slicing software because it's layer by layer. And it looks at how it'll gradually grow those parts using a base material in a controlled setting. Those materials can be something like a liquid resin. So stereolithography is a great example for that, and usually have like kind of liquid resin, smoother look to it. It could be powder bed. So think like a flour fine powder for plastics or metals to grow parts used typically using lasers or some heat process. And then filament base. A lot of you may be used to this. If you think 3D printer, you may think about that printer that's nearby you right now on your desktop where you have that spool of plastic filament melting down and zigzagging back and forth. Very popular. We call it FDM. But each one of those has this raw material. The raw material kind of executes the output, and we're going to go into more details about that later. So what drives cost though? It's the making of the parts, right? It's the volume of material used. So if you're making a brick, you're paying for that full brick, right? But if you're making something that's kind of lighter weight and latticed out, that reduction of volume using that part will reduce the price of that part. Machine overhead, we are typically running industrial additive manufacturing. So instead of machines that cost hundreds of dollars, most of our industrial equipment costs hundreds of thousands of dollars. So it has a labor rate, it has a factory footprint, it has staff behind it, and that overhead can often be the driver of cost, especially in prints that take a while to make. So if you have a 100-hour print, for example, you're going to be paying that labor rate against it, and it's probably going to be more expensive than the material itself that you're running those parts in. And lastly, secondary finishing. Some finishing, like tumbling or automated bead blasting or even chemical vapor smoothing, is a automated batch-based process. Other finishing, anything that I'm sanding, I'm painting, I'm drilling, I'm installing inserts, you're paying a labor rate against, and that'll drive costs on a part-by-part basis. So it's definitely something to consider when you think about scaling in additive manufacturing. But what can I do with this? I don't need a tool. I don't need to tool up like injection mold to make plastic parts, or get large stocks of material and then machine down in with a CNC machine. This is the winner when it comes to low volume work and prototyping. You're directly digitally manufacturing your parts when you're using 3D printing. That 3D file is being interpreted into build setup software. That build setup software is sending that information to a printer, and the printer will do its best to make your part. Because of this, the turnaround's very quick. You don't need a minimum, so you can serve a customer of one with 3D printing, and you get parts within days, typically on order. And the designs, because I am growing those parts, and Matt will talk a little bit more about this later, you can be more function oriented. In CNC machining, leaving material behind is good because it's less work, less cutting to be done. In additive manufacturing, you could really make specific designs and make decisions on your designs to orient towards function, which is very cool. And again, because it is just a 3D CAD model, it's the lowest barrier to entry next to one other process that we offer. So sheet cutting technically wins because sheet cutting, which is I think laser cutting of a flat sheet, just requires a line drawing, a DXF file. But you add a third dimension to that, and now you've accessed the entire 3D printing landscape. So this is how we see the world at Xometry, right? The world of manufacturing, this is plastics and rubber, but we see manufacturing as a continuum. Because we're looking at a diverse amount of shops and services, we're able to kind of see where different technologies lie within this continuum. If you look from left to right, I'm looking at low volume, think like one-offs or prototyping, up to kind of the dozens of parts, dozens of hundreds of parts, and then moving all the way up to high volume production. If you pause right now and take a peek around you, not my desk included, but take a peek at your desk, you may find that most of the plastic components on there are probably one of these processes, like injection molded, extruded, compression molded. I forgot thermoforming, but thermoforming would be a great example there as well. Um, so ultimately, if you're serving like the hundreds of thousands or millions, you're typically in that world. But there's a lot of service needs that hit this middle ground where additive manufacturing can often meet or surpass where you may be typically urethane casting, which is great for that 5 to 50s unit, or using plastic CNC machining. You may be able to find alternatives and advantages in additive manufacturing in that realm. And this is just a quick list of technologies offered at Xometry. So when you go to our instant quoting engine, you can see, CNC machining, sheet metal, sheet cutting, very bread and butter for us, as well as additive manufacturing. And then the formative processes, think plastic injection molding, metal die casting, metal stamping, and urethane casting extrusion processes. So regardless of where you are in your product development life cycle, whether you're still making that part or you're looking for a new supplier of something you're sustaining, we usually have an option to meet you there. But I am talking about 3D printing, which turns out is not just one thing, it's a lot of things. So with 3D printing, we have different verticals of technology. What they have in common is that additive manufacturing side. So I'm growing parts using a digital file. The most popular processes typically are these ones on the left here. We'll talk more about those as well, but we usually think of them in different categories, plastic and metal, as well as under plastics, we typically have thermoplastics. So something like ABS or nylon, where when I apply heat, it goes into a liquid state, it cools, and now it's a new shape. That's going to be a thermoplastic print. Thermosets. I think if you've ever had a cavity filled where they have to shine that UV light in after they put that liquid or paste in there, that's going to be something like a thermoset material where it hardens and catalyzes with exothermic reaction. So think about resin photopolymer printing, for example, very good example of a thermoset or resin-based 3D printing process. Both these metals use a powder-based process, but they have different ways of making the metal part solid. Direct metal laser sintering uses a laser to selectively melt areas on a build chamber and build a part bottom to top with a very fine metal powder, kind of being fused down to a build bed and growing from there. Metal binder jetting uses a glue binder and then has secondary processes, so it'll make the shape kind of gluing layer by layer, creating a green part, and then you go through several stages in order to take that green part, move it to a furnace stage, and then it'll actually sinter into a metal part. We see that these four on the side tend to be the most popular amongst our users at Xometry, and because they have a lot of advantages when it comes to cost competitiveness, design flexibility, and choices in materials and performance. So SLS and MGF are very similar to each other. They both can print mostly in nylons, but they also have polypropylene and TPU and filled materials. But they have a unique ability to nest in multiple dimensions. So I don't just have to think about my parts stacked on the table and saying that's my build. I could actually put many parts, building 30 to 300 parts per machine per night. So you have a lot of production viability. FDM is this fused deposition modeling, that kind of spool of filament that's printing those parts, has that boutique aspect where I could actually choose the plastic and the color that I need for that. And if I need a scale, I just get more machines. I make an army of them to produce parts on demand. And then stereolithography is the OG 3D printing technology. So SLA is a technology that will use UV light to cure liquid resin on a layer by layer basis. And there's been this engineering resin revolution that's been happening over the past 5 years, where I used to think all SLA was just brittle stuff that, you have it once and it breaks on you. Now you have real high performance, even UV withstanding materials that are being built within this process. But every single one of these, and Matt and I were talking about this when we were practicing, every single one of these is their own webinar on it by themselves. So I will move on, but always happy to answer questions about these processes later. So yeah, with that, I'm going to go in the design fundamentals, and then Matt is going to help kind of cohese it together a little bit. So we've been talking a lot about growing parts, And when I have this little animation here kind of showing a a part looking at it from a section view going on that layer by layer basis. I find myself doing this a lot. When I'm changing my mindset on making a part for 3D printing, making it that design, I'm using a section view a lot and kind of thinking about it by orientation. How am I intending to design my features so they grow with each other using design best practices? You're going to get in this mindset a lot when you're designing your 3D printed parts. The other side of this is that additive manufacturing machines, they are doing their darndest to make your 3D digital design, but you cannot stop them and tune a feature like you could in CNC machining. So for example, say a hole is a very tight tolerance, I can't run that operation, stop the mill, go inside, measure, adjust my offsets, and then cut again and check it out. Out of manufacturing, the machines are calibrated using essentially calibration pieces, calibration cubes, and then you're producing those parts with standard scale and offsets to them. They there are machines that are more accurate than others, but all of them are considered producing a near net shape. And that's important when you think about your tolerances and how you're creating your prints for 3D prints. And lastly, it turns out we're not in space. Gravity still exists. Support structures are very common within additive manufacturing. So most processes require support structures. And what they are features that are sacrificial that are built with your part to hold overhangs. So if your part is like a T shape, for instance, and I'm building it kind of like as if it's standing up like a piece of text, I'd be building sacrificial features that are going up to hold that overhang of the T at the top there. Then they get removed after the build. This picture here is probably the worst example of showing a lot of really strong supports, but it's very visual for a presentation to show these little nubs here where that sacrificial support structure was removed. And we talk about these base materials a lot. And again, this is getting yourselves in the mind of additive manufacturing. Resolution is very process dependent. I like to use my Sharpie and mechanical pencil example when I talk to my customers because of how this may affect your design and even like the design tips we're going to talk about later. How you may, for example, in a powder bed process, want to make a larger hole than something that's you're able to do in a resin 3D printing process. So I always like to think about powder bed fusion when I'm putting a lot of heat against a metal or plastic part or plastic material to fuse it together as a Sharpie fine point. It's got decent resolution, so that's why I use fine point and not a marker. But if you linger anywhere, you're going to bleed. Like you're going to get that ink bleed. So if you look at my Sharpie fine point, that little circle right there, it's kind of filled in. Like it's even though there wasn't supposed to be material there, that bleeding, that extra heat that's radiating out there actually would fuse that up in a process that's especially at a very, very small scale. When I look at UV cured resins, the resin itself, like the liquid resin, typically has a liquid look at the end, and you have really great detail and clean edges. So it's typically the best resolution processes are going to be resin-based 3D printing. And then lastly, that filament-based 3D printing, it can sweat the small stuff. So I don't even loop on this, right? I kind of go close together and pinch and then move out. I am zigzagging a filament, a melted filament back and forth to create my layers on a layer by layer basis. And with that, it has more coarse features. But one of the great things it can do is it can build large, broad mechanical structures really well. But if you have something that's very high detail or has very fine features, they may be sacrificed. And I'll show you what I mean in just a second here. So this slide, I'm calling it the Who's That's Pokemon slide, but we're going to go through our different examples of powder bed, resin, and filament. So first off, let's talk about multi-jet fusion. This is a plastic powder bed fusion process. The parts start with a white nylon powder. Layer by layer, it's fusing that using essentially a ink mixed with heat to create a selective fusion. And you can kind of see, like if you imagine this T right here is 10 millimeters tall, you can see how the finer details, like there's actually a smaller text there. I didn't even resolve on this, but you see the small features kind of have a rounded look about this, and it's a little fuzzy, but I could still read it. It's still pretty good. but it has some fuzzy features to it. When I look at this compared to a liquid photopolymer, I have much crisper details. In this case, again, that's 10 millimeters, 15 millimeters, 7.5, and 5 here. But you can see that the smallest text actually did resolve in this. I don't recommend making all your text like this, but you can get away with it better in SLA. But you can see that you have much more crispy features from the get-go with this process. So better feature detail resolution. And then lastly, I'm not knocking on FDM, by the way, because it's an extremely versatile process and we print a lot of parts in FDM. But if you're doing small text, 7 millimeter text or smaller, it probably isn't the best process for you because you could see that that kind of line stroke, right? So you could see that filament and how it's deposited on these parts. And the more gradual that curvature is, the less steep the slope is, the more coarse it looks. And as it actually is going more vertical, you tend to get some better results on it. This is probably like a worst case scenario print, but I really used it to emphasize the differences between the different outputs. So depending on your part design, you may be going to one process loop versus the other. And that brings us into this paradigm of function and finish. Every single 3D printing process has its own outcome. It has its own set of materials, its own detail resolution to it. So when we start thinking about what I want to do, like what is my goal for my project, we're going to be talking about what processes should I start to down select or look at when I'm thinking about my 3D printing design. If I'm looking for something like aesthetic, cosmetic, prototype, I'm usually looking at what details I want to do. Like let's spin the cat. Let's talk about those parts. If I see small text or features, I'm probably going to put you towards a resin-based 3D printing process. Clarity, by the way, resin-based prints can make clear parts. So it's really the only place to go for that. If you can print in clear filaments on FDM, for example, but you get a very diffuse part for that. Um, smoother parts, you have a few different options available, including some secondary processing for SLS and MJF. But anything that's just general prototyping, honestly, SLS and MJF, we could do a whole webinar on when not to choose it because 90% of the time, those are probably going to be your go-tos if they fit into the build area. So in this case, we have an example of I want a clear part, SLA, clear view, quick clear works really well. On the other side of this, a lot of what our work is with mechanical engineers. We're making stuff that does stuff, right? So we're looking for functional parts. We have a few down selects here because we have our menu is very well oriented towards mechanical components. The first question is it going to be metal, right? Because I only have a couple metal options, so metal is a very quick down select. The second is, is this going to be rubbery? Like, is it a Shore A value? We have a few different processes that have a Shore A value, so we could print rubber or rubber-like components. If it is just going to be a rigid plastic, then the question is, what's it going to do? Does it need to withstand heat over 150 Celsius? Does it need to be flexible? I mean, ductility. Does it need to pop into place and pop out? Chemical resistance, impact resistance. All of that can be a down select criteria for you. And then under each one of these umbrellas, we have a variety of materials that can fit your need. The last thing to talk about is when we talk about these 3D printing platforms, they are platforms, right? They're physical spaces that have capacity limits. This is a general overview. I know, like Matt, we've raised our hand on this. You could comment on that in a second as well. But in general, like DLS and DMLS platforms kind of cap out at that 9-10 inch range on part size. Selective laser sintering and MJF has a sweet spot around that 12 to 13 inch range or smaller, as well as metal binder jetting is kind of in that world. And SLA and PolyJet, those resin-based processes can go larger. So 24 inch is kind of like a sweet spot cap out for that. But FDM typically has the largest format. And that's because it has a lot of stability. It's building on a big flat build plate. And we could casually print parts up to 36 inches with the machines that we have. And Matt, I'm not sure if there's anything else you want to say on this slide here.
No, yeah, we pretty much categorize the systems and the materials into general commercially available off-the-shelf type solutions that we can rapidly provide that are repeatable, reliable, always available. Yes, there are machines that are much larger and can do much different things. We have some of those. If you don't see anything here in this slide stack, doesn't mean we do not have access to it. Just means we might need a consultation to talk about it a bit. Feel free to contact us.
Yeah, I got a drawer full of really cool parts from processes that we don't offer right now, and we want to add to our marketplace as they mature. So yeah, Matt, I think this is your rodeo now.
Yep,
So
you need
like,
a
how do
break?
we add value? Yeah. Oh yeah, I need to take a breather now. Thank you.
Right. So as Greg was explaining here in the past, some the different options, the different materials, different platforms. There might seem like a lot of options in 3D printing, but I'll be the first to say that just because you can print doesn't mean you should. We need to have, there needs to be a driver to print parts. Looking forward, as additive manufacturing is just another tool in that toolbox. That's why we carry over 20 different manufacturing processes because additive is just one of those tools. But you have to think about using additive moving forward into a design, not looking backward. It's always better to look forward. So when you look forward, you can add value to your design with the built-in inherent advantages of additive manufacturing, like lightweighting parts, huge in aerospace, using optimization software to create advantages in buy-to-fly ratios, custom lattice structures that can lightweight parts while keeping them maintaining superior strength. With that comes design complexity. Lattice structures, gyroid features, things like that, they are not simple figures. They are not easy to manufacture. Hence, advantage additive manufacturing. Customization. Pretty simple photo there of customization. It's just the Xometry logo. But that just goes to show, you can serialize parts. You can create patient-specific parts. You can add logos to your parts. You can add scan codes and things like that to your parts for all different types of serialization. So customization is very handy with additive manufacturing, adding more value. Design freedom. Just because you have one idea in your mind doesn't mean you can't print three or four. Let's look at generative design. We're going to talk about that really big with these CAD packages out there nowadays, creating lots of iterations of different types of design configurations. And with lucky with additive manufacturing, it's rapid. We won't forget about that term rapid prototyping. We can print a lot of parts really fast, so you can go through iterations faster, get to your end goal, get to market faster. And then also, let's not forget about part consolidation. I once heard from somebody in additive manufacturing, it wouldn't be an additive presentation without mentioning the GE fuel nozzle. The GE fuel nozzle was a huge part consolidation with DMLS. That added value with additive manufacturing, huge value. So that's just a great example of part consolidation for additive manufacturing.
By the way, I always, when we did rapid prototyping in my early career, one of the things we did for that multiple design iterations, we call it the shotgun approach, right? So we were working on grips and things, and we would basically print 5 or 6 slightly variated iterations of that in one build overnight, send it over to our stakeholders, get their feedback like that same day, do some modifications, print a few more, and it helped us really narrow down on that need very quickly before we got in the state of production. So it's just super, super useful to do.
Yep. And you can see, as you're looking at your design intent, where you're going to be in the future, is it going to be 3D printing? Greg had that great slide earlier that kind of showed additive manufacturing right in the middle of that the road to production, so to speak, slide, where we're right in the middle of that production range. And how those costs shake out is going to be important to your costed bill of material at the end of the day. So, we're looking at kind of complexity versus cost in 3D printing and traditional manufacturing. So we've got just a simple 3 by 3 by 2 volume type of geometry, and we've got a traditional CNC and then 2 additive processes down the column, and then across the row we've got various volumes of infill for those various geometries. And what's interesting is you can see with CNC, Obviously, like Greg mentioned earlier, tool paths cost money. So the solid block of material is going to be very inexpensive in CNC. And there used to be the presentation pitch. I keep on going back to my historical notes from over the years. Complexity is free in additive. Not exactly, but it does prove a point here where you're moving across with CNC and you're adding complexity, you're adding cost. If you look at DMLS or SLS in the additive process, as you move to the right, you're decreasing in cost. It's adding complexity. It's not exactly free, but you're removing runtime, you're removing material volume, removing energy consumption, therefore parts become cheaper. That's your scale of economy with additive manufacturing and production. It will bottom out pretty quickly, but as additive continues to industrialize, this will improve.
Absolutely. And I always thought it was interesting. So I have this shelled in the middle here. So this is just less material. So you see this drop right here because it's just lower volume than the quasi lattice. And yeah, just that volume really does drive the cost there. So we're going to get some specifics now, talking about design tips and tricks. Something to note is I have a lot on these pages. I'm going to talk more about the overview and how what we see on the Xometry side. But we can always rewind and go back, especially in the Q&A section, to talk a little bit more about a specific design tip or trick, because we see a huge variety of these. And I do want to talk with the biggest pain points that we have when we receive parts. The number one reason why we call any customer after an order is submitted in additive manufacturing is a thin feature. That's going to be typically, thin wall features or like thin pin features or gaps and holes that won't resolve properly within the process selected. These are some general guidelines, but something really to look at is we consider walls in two different ways, unsupported and supported. So unsupported wall would just be a direct cantilever. We really want those to be at least 1.2 millimeters thick. 2.5 millimeters is better for a more coarse process like FDM, especially large format printing. But just know that walls below 0.5 millimeter, they won't resolve or they may easily damage. So does this mean that printers can't make parts under 0.5 millimeter? No. But what it means is most parts are not benchmark models. Most parts are not cool little tests to show off the capabilities of a printer or something. Most parts have some function to them. They need to be handled, they need to be installed. And keeping within these guidelines is going to let you make a functional part that won't break the second you open up the box. Supported walls can be a lot more forgiving. So when you think about even designing walls with a curvature, a T shape or C shape or X shape, you are adding additional beefy structure to that design. You can go a little bit more broad, a little bit thinner on supported walls because you have something else that's helping it along, helping it resolve and survive. I have this little design here, kind of showing a thicker wall. It requires less of a backbone. In fact, this could probably stand alone just fine. But as you go along with the thinner walls, you're building more of a support for it. So less cantilevered material and more support for it to resolve and survive handling and use. Holes, a few things you need to look at is detail resolution as well as the process in holes. If you have a thermal process, holes tend to shrink a little bit with them. So if you have a hole smaller than 1 millimeter, it may not resolve fully, or you may not be able to stick that pin or have that use. If it's a vent, maybe you're okay, but if it's something more functional or mechanical, you definitely want to go above 1 millimeter and work with those guidelines. The larger aspect ratio of that, the larger the hole you want to have, because there are things like it could just be one location where there's a little bit of a little bit more of a shrunken hole, and that could ruin your entire application for making those parts. Gaps and clearances have very similar roles, and if it's easier to clear, you can be a little bit more forgiving in your design. If not, using the general guidelines, about 0.5 to 1 millimeter is usually a good minimum on what you're using. But in general, if you're designing for injection mold design, coring out those objects, using ribs for stiffness and strength instead of thickness, all those design features are going to help you with additive manufacturing as well. So a mental model, especially with that uniformity for injection molding, works really well here. You don't need to worry about undercuts or draft too much, but they can help. So when I look at features and text, for example, text is just a series of thin gaps, thin walls, and these wires or pins. So think about text as features, not font itself. But usually minimum feature size, 1.5 millimeters is usually my go-to. And if I need to stretch the limits, I'll go a little bit thinner to 0.5 millimeter or so. But beyond that, you're gonna have detail loss. Like a good example is that powder bed fusion design I showed earlier. You kind of have more of that fuzziness that comes out of it. Um, Wires and pins, they can have trouble printing themselves, especially if they're too thin. So 1.5 millimeters is a good minimum. But look at that aspect ratio. So like the 5x aspect ratio there. The thicker, the better, or adding something that protects them. Because it's not just can my printer do that? Again, most people aren't printing benchmark models. Most people are using 3D printing to do something with it. You want something that protects those features because a wire pin is very vulnerable. It could snap like a pencil if it gets hit in the wrong way. Sometimes I call a pin in the wrong place on a 3D print design that's otherwise perfect a god pin because if it breaks, your entire part is scrapped. That's where I ask, like, maybe you should, maybe you should make that into a sacrificial feature or use a metal pin and make a hole there, something to take that vulnerability away in your design. Um, so we talked a little bit about text, but engraving and embossing, kind of the same thing. 0.5 millimeter is usually enough to get you definition. 1.5 millimeters is pretty good, but you don't really need to go too much further than that if you're doing either engraving or embossing, if you're just trying to show a logo or a feature. And just know if I'm thinking text, also think sans serif text. So Arial font, for example, is fantastic. And like I said, we're going over these. I see some questions coming in, so please keep on asking away as well. So when we talk about features, the other thing we need to consider is that support structure, right? So we've been talking about growing parts, near net shapes, and support structure. I I can build features on a design that do not require support. This is something where usually I'm using a 45-degree angle will help out a lot. So I have, for example, a little kickstand design here. My kickstand, just notice that it's a bunch of 45 triangles. So I have these features building off naturally. I have text on this. My text is popping off at a 45 degree. I have my logo on it. My logo is popping off at 45 degrees. So if I build this orientation here, everything is a self-supporting structure. I could get away with a little bit of an overhang, no more than 2 millimeters. Bridging, so if I have something, think a little keyhole or archway or something that's going to be printed with that bridge parallel to the build surface of a part, that's you don't really want to span more than 10 millimeters. But even that, like we may require support structures for. Um, just know that this is more important, for example, in metals, where your support structures are metal too, and they may be harder to remove. The last thing, I'm putting never down on knife edges. Additive manufacturing is a process where you're using a smaller base to build something up. Think about it as a bunch of little Legos. How many Legos do you need to stack together to get a knife edge? You'll never get there, right? So when we try to grow a knife edge, like something that's overly acute in a design, you're going to have either a feathered look or unresolved features to it. I recommend popping a 0.5 millimeter chamfer on those edges to get a cleaner, more consistent look that's going to look the same build to build in that design. Lastly, just general tips. So how do I kind of clean up my design on this? Fillet everything is really a really good design rule. So typically, if I have something that's cantilevered off of my part, if I don't have a fillet there, then I have acute stress points right at that joint. If I put a fillet there, it just helps even out the stress, making that feature much more robust. I also add drafts. So if I'm making my text, I usually add like a 3 to 6 degree draft on my text or any protruding feature. It still gets me the cosmetic needs that I want from my design, but it gives me a wider base. So it kind of beefs up the base of that design to allow me to have finer features at the end where you're going to be perceiving that. Draft is a really great tool, especially when making text in your design or any type of logo. And clearance channels are something that's really important for liquid-based processes as well as powder-based processes. I typically am post-processing with blasting, like I'm blasting beads down into these parts to clear them out, or I'm using like a water jet or something to get out that material. If I have a blind boss, so screw hole that just ends there, it has uncured or unsintered material within that. If I'm trying to blast it out, it's all I'm going to be doing is packing that material down to the base, and I may need to use a toothpick or something to help clear that out. If you add a little exit hole right at that base, it's going to give a channel to let air flow and clean out those whole areas. So it's really great when you think about designing for additive to add those exit holes. And because we have that freeform design, it's not a bother to the part design as well. And I'm sure if you had a Matt, if you had anything to comment on those designs, I know like we went through some of those, especially on metals.
Yeah, increasingly important, to consider support structures when it comes to metals and considering part orientation when it comes to your DFAM approach, your design for additive manufacturing approach, which will help you look at support structures, how they can be removed, where they're going to be contained, and if you can get away with utilizing them or not utilizing them. But we'll talk about a tool coming up here that can help eliminate some of that for you.
Absolutely. And yeah, we'll get there in a second. But the last thing is there's stuff that you could do to after your print. So everything I've been talking about so far is will my print bake and will it survive the post processing? So you can do what you can do better, like in file preparation, you can add textures to your print. But then secondary things, I could do finishes like adding cosmetics like dye or chemical vapor smoothing. So what is a texture? Texture is something that's digitally applied. This is different than texturing a tool for injection mold, for example, where you're adding that feature to the tool. This is something where your CAD file will have those features to it. This mouse, actually, I was playing around with a Formlabs tool that came out called Meshy, and I added some snake skin to my mouse cover here. And so I designed my original design, which you see on the right-hand side, and then I applied a digital texture to it. And what it can really do is it can help mask features. So it can help mask, coarse layer lines on your design and give you something that has more of a professional cosmetic look to it. Even a fine matte texture, especially with a resin print, can give you a really cool look to that, and something that gets applied before you load the part up to those designs. Dyeing or paint can give you the colors that you're looking for, and chemical vapor smoothing can also help take some of these plastic parts and bring them to the next level, getting them almost an injection mold-like quality to them. The other note is when I think about threads, threads are, again, a series of thin walls and thin gaps. Things happen there, but what can I do to mitigate that in my 3D print design? Using threaded inserts. So when you're designing for a 3D print, you may move to use, for example, brass screw to expand or heat set inserts are very, very common. And it's something that auto quotes again on Xometry site. So I'll go over this, pretty quickly. And again, I see questions coming in, so please keep on asking questions. That's awesome. So CAD files, we usually like to accept something under 100 megabytes. If it's over 100 megabytes, you probably have exported it at too small or too high resolution. Like you have a resolution that won't actually change the outcome in the physical printing world. We do like step files over other file formats because the world is your oyster. You can use step for all sorts of manufacturing processes. But if you do need to do a mesh file, the format 3MF is really great because it can hold, first off, it has a smaller file size towards complexity, like it's much smaller than an STL file. And also going to hold stuff like color data. So you can add color and textures directly into a 3MF file, and we have different printing processes that can make those types of parts. Other things is when you're uploading a technical drawing, if you do have a technical drawing for your need, use our manufacturing standards. You can find that at xometry.com/manufacturing standards. That's going to show you the general outcomes, and that should be your title block. You shouldn't be using CNC tolerances against a 3D printed part. We want to make sure you manage your expectations. And on this list here, I mean, we've seen a lot of great outcomes with Fusion, SolidWorks, Onshape, NX, great CAD software out there. If you are accessing free software, just make sure that you can export it as a step file because step, again, is a universal. It's like the PDF of 3D file formats. And for 3D printing tools, I have my toolbar GrabCAD Print and Formlabs Preform right now, alongside with other professional tools, because they help me simulate and visualize a build of something for a very quick gut check. They're free to download, and you can go and take a look at, for example, FDM or other processes. And Formless Meshy is an online tool, and then Microsoft 3D Viewer, believe it or not, great way to verify parts, especially if you had color. Matt, do you have any comments on that? What do you see?
Yeah, absolutely. A simple software like GrabCAD is going to enable the part to be sliced and create support and generate a support preview for you that you can step through slice by slice to find out where you might have issues with your print. Thin wall conditions, trap support, too much support, too little support, downskin angles. This, step through slice by slice will help you create a better 3D printed part and a better 3D printed design.
Yeah, absolutely. And I do have to say, usually if you have a desktop 3D printer at your work or home, you are typically are a better designer for additive because you probably already broke it apart by accident or had a build fail because of a design feature. So that empathy built with having a desktop printer can actually go a long way in your design process using more industrial equipment.
All right, so let me take this one. Let's add some automation and some horsepower to your design. So if you're fortunate enough to have like a seat of, Siemens NX additive manufacturing software suite, you would be empowered with some really awesome tools, and part of that is generative design. So generative design is going to be, defined as a computational iterative design process. It's going to use computing horsepower and algorithms to create a wide variety of CAD models and possibilities, CAD and shapes that are driven by user defined specifications. Material, space limitations, loading characteristics, could be part orientation, static mounting points, dynamics, things like that. This is going to automatically generate these different CAD models for you that can be optimized for specifically additive manufacturing. You can see some of the topology optimization come in as the iterations go from left to right on that mount. So you can see, this is only possible in a 3D printing situation. And on the upper right-hand corner there, we've got an example from Formlabs that shows a welded assembly that is transformed into an additive manufacturing component that is consolidating those parts, optimizing material usage, and then coming out with, a really organic design that can only be, 3D printed. This is where you're adding value to additive manufacturing and creates huge value. Again, NX is a great, platform for this, but there are others. Fusion 360 has one. There are others that you can find that will help you with a generative design technique and focus on additive manufacturing.
Yeah, absolutely. And what's great is that list is getting longer every year because I'm a big proponent of generative design, but accessibility is always a challenge. So right now, it's very much seasoned engineers are having access to these types of tools. But even like I said, like Matt mentioned, Fusion has a generative add-on now. It costs something, but it still gives you some really cool results. But it's that cool idea of saying, here's the thing I wanted to do. Here's the areas it needs to attach to. Here's my keep away zones. Make it. Like it's prompt engineering for a 3D space. So great time to remind you all, submit your questions. I got a few more things here, and we're going to jump into questions and answer in about 2 minutes here. But yeah, we've talked about this. We make a lot of parts. We make so many parts all the time in over 8 different additive manufacturing processes. And we also have that holistic view of other processes, so we can help you graduate if you need to, or design and optimize if you're looking to stick with additive for high performance production parts. The best way to get started is Xometry's instant quoting engine. Go to Xometry.com. You can log in. It's a secure upload, so you could upload your 3D file, and pricing happens in seconds. So that is, 97% of the time, you're going to be going using instant quoting engine and starting your quote. And you could go get your pricing, change your quantities, configure your options, and press buy. And it's a very e-commerce checkout for something that's usually a headache for manual sourcing. We also have our request a manual quote option. So we have a manual quoting team, and Matt sees a lot of these too. But that's something where we may be helping you set up the quote, or we're turning around that quote because of a custom finish or a custom inspection requirement or a material that we have access to but may not be instant quoting our menu. we're always happy to explore those options with you. And then the third part, and this is how it usually happens after we've already gone through steps 1 and 2 with you, is if you're in a production level program, say you're a drone company or an autonomous vehicle company, and we've helped you build certain aspects of this. Okay, I need to serve my customers. I have demands needed for my assembly plants. How do we build a structured schedule? That's where we may work with partner engaged quoting to reach into our network, find the best solution for you, and help engineer that sale to make it work with great outcomes. And we have a lot of resources. Like I said, every single process is its own design guide, its own webinar, its own everything. So we like to put a lot of resources on Xometry.com. We have, of course, webinars and recordings like we're going to have for this event here. We just launched our design guide for stereolithography, so that is brand new, freshly published, or republished, I should say, but updated for 2025. So that's available right now. You can go to our stereolithography capabilities page, and also our email follow-up. We're going to have a link to that as well. And you can always check out our blogs, product updates, or case studies. I know Matt has a really great resource tool as well. We have these quick design references page. So if you go to Xometry.com, go into search and click or search for quick design references, you're going to see these one pagers per process that we have for you. It's super convenient. And just lastly, if you haven't checked us out in the last month, check us out. We've lowered a lot of pricing. So June has been a 3D printing month for us. We've lowered our pricing on selective laser sintering. We've added more competitive offerings using Formlabs for SLA, added more competitive offerings under FDM, including international options, and lowered our pricing on multi-jet fusion. So our most popular processes have all seen decreased pricing. So we're really excited to have that. Oh, thanks. Yeah, Matt just put out a link here. And lastly, check us out. Check out the website, and we also have a code for you, additive webinar 10, that you can use on your next order. And with that, let's jump into some questions here. So I have a question. Does shrinkage affect final parts? Do you want to touch that, Matt?
Sure. So any type, yeah, of course, polymers shrink, especially when they're heated and they're cooled. The slicing software and the computational software that's provided by the OEM has an automatic scalability factor for the parts when it comes to printing and cooling and post-processing. So you don't need to worry about that on your end. You submit the part that you want to see. It's very WYSIWYG. What you see is what you get. So once you send us a CAD model, that's what we're printing within parameter tolerances.
Yeah, absolutely, and that's what we hold ourselves to, is that manufacturing standards. That's going to be the manage your expectations of what you're going to get when you press print. So absolutely, look at the standards over the worry about what this process is going to do. We manage a lot of that digitally on our side.
Mhm.
All right, so I have a question. So it's a question on warping of SLS parts, but they're talking about metal. So I'm going to say like a DMLM or DMLS here. Large flat parts printed in stainless steel 316 have a tendency to warp. If I
Yep.
have ribs on the 3D model and plan to machine them away myself, after I receive the part, will that help? Or will the part spring back once the ribs are gone?
So the key is here, this is orientation related. It's got a lot to do with the geometry, and we talked about ratios of walls and ribs and things like that. So, I mean, the thinner you get, the more difficult that's going to be to keep straight because, ultimately it's using a lot of heat. I mean, that is a mini foundry going on inside of a DMLS machine that is reaching 4,000 F. So there's a lot of heat that's going on inside of that machine. So every time you slice that model, there is volume to that slice across that broad surface that you just created or you're laying down. So if you imagine, if you just wanted to create a piece of sheet metal that was a 1/4 inch thick, sure, we can print that piece of 1/4 inch thick sheet metal, but you don't want to print it flat. So you're slicing all that volume at once because what happens is you're going to repeat that process layer by layer by layer, heat upon heat upon heat upon heat. And the more that happens, the more that is going to create internal stress and deform that part. So you want to angle that part up on an angle, tip it up on an angle, the angle of repose. It'll be an acute angle. It might need to drive some support, but in this case, you are taking less volume per slice. You've got less heat per slice, and you will get a much better result. If you have to, stand it straight up and, and ask us for advice on how we can help you with orientation to create a better part. Same thing goes for the polymer side. There's no difference. It's still heat and polymers. It's just heat and metals.
Yeah, absolutely. And something that I realize is because you're building on a layer by layer basis, you know, when that first part of that part may have started 20 hours before the last part of that part's made, right? So there's a lot of heat stuff that happens in between. That's where supporting strategy and orientation plays such a big role. You're also talking about like, parts springing back. Parts can be in a stress condition. The metal parts, we can run an annealing cycle. A lot of times, larger parts, we're going to do that anyways. On the build plate to de-stress them in a fixed position before the supports are removed.
Mhm.
Not as important on smaller parts, but for larger parts, yeah, they could dance on you. And I have seen, when we talk about printing bricks and why you don't want to print bricks, stress is so powerful. I remember
Yeah.
printing a tool block for someone. This is back in like 2015 or something, and it ripped itself out in half. It literally stressed so much that it ripped its own body in half. And what we ended up doing was actually coring it and latticing it, and then it printed
Mhm.
perfectly.
Yeah, it's funny to say you almost use injection molding principles even when it comes to metals.
Absolutely, absolutely. Metal DMLS on a diet, way to go. So let's see. So David asked a few questions, but I actually see something about keying together, and I'm gonna focus on that for right now. Um, so, and I'll answer some of these others offline. But when I'm building keyways or slots, I think it's really important to understand those manufacturing standards. So, say I have a hole with a key in it or a spline feature. We know typically in heat-based processes, those holes are going to shrink. So our design guides typically have a set offset, like offset by 4 thousandths of an inch or 6 thousandths, in order to make that hole a little bit larger, because we know it's going to shrink, and that's usually going to be a better fit than just printing it as is. If you have multiple parts keying, sometimes it takes a little bit of tuning to work those together, or you want to tolerance them in a forgiving manner to do that.
Hmm.
Do not design flush to flush. Don't design the flush to flush in regular manufacturing either. But there are ways to do that, but sometimes it does require a prototype of your prototype. Something really cool that you could do
Sure.
is slice your file and just print that feature and see how that feature works. So you don't need to pay for the full print if you're just testing a small piece of that feature there, and that's something that's
Mhm.
very easy to do with additive.
Right.
All
Absolutely. And a quick pro tip on that, document everything you do. On a detailed drawing, document what material you used, what machine you used, what process, what the material, part orientation, pack density. Document as much as you can to make your part repeatable and reliable in the future, so you don't have to reset and do it all over again.
Yeah, absolutely. All right, I got one. So you offer stereolithography. Do you also produce ceramic parts? If so, what resin slurry manufacturer and is it manufactured in-house or external suppliers? So true ceramic printing, we have some discovery on that, but it is very touchy because ceramic parts often will shrink about 25% or more from their net. And what I'm talking about is true ceramics, like going to be in very, very high heat conditions. But a bread and butter everyday use, actually, I got stacked right behind me is ceramic filled resins for stereolithography. So all of these auto quote on Xometry site, but these are really good for kind of test jigs, fixtures. If you're doing like what's it called, a wind tunnel testing, for example, don't expect flex, but expect very, very high stiffness. So I have Acura Bluestone here. I have Formlabs. What's this? 4K. Um, or no, sorry,
Rigid 10K.
Rigid 10K. Yeah, it's Formlabs Rigid 10K. And then I have Soma's Perform. So we have different brands as a marketplace. We can bring competitors in one place, and you get to press buy with them. But if you hear them, you got a much more of a ceramic kick to them. So they're going to have a lower heat deflection than a true ceramic, but still higher than most polymers would have for those needs. But it's a great option. That's not quite true ceramic, but true ceramics are a little bit tricky on a part by part basis. A lot of times they require tuning and iterations to get that part one may actually be part five. So it's a little bit tougher to launch. All right. Let's see. Uh, t- 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 Andres had a question about components within the U.S., how much is typically manufactured in the U.S. Honestly, we just started adding international options for the first time on additive manufacturing this year. So wholeheartedly, our manufacturing base is U.S. domestic, and we've added some international options for SLS and FDM recently. But we have a very robust manufacturing base. In fact, actually within the U.S., we work a lot with export restricted items, so ITAR and EAR work, and that's a checkbox on our website. So we work very well with whatever your needs are. You get to see where your parts are being made, like so you can choose. You explicitly are choosing domestic or international. We're never going to surprise you with that. That's a part of the power that we have with our instant quoting engine. All right, and let me see. Oh, I got a good one for you, Matt. So for large parts, is it more cost effective to print on a large format machine or break the part into sections with mating features later and then glue or sand or bond?
Well, that would depend on a couple of specifications or, requirements. One being tolerances. Of course, when you print in different pieces, you're going to have a different stack up rate. If parts are plus minus 15 thousandths for each parts, you're going to have much more stack up than building, a larger part. The with such processes like FDM, you can take advantage of custom infill percentages. So with large parts, that's a huge cost savings when it comes to printing one large part versus smaller parts. You will have less material volume going into that one part, so your cost would be less there. And then also, of course, you've got less labor into post-processing each individual part rather than one large one. Again, we've got some large systems out there. We can accommodate some big things. We can also do split and bond, where,
Mhm.
just ABS with ABS cement works great. That's what it was made for. So we can do a various array of assemblies or, individual parts and large parts as well. So we can help you draw a line in the sand and figure out what that cost, competitive nature would be between each.
Yeah, and something I recommend there is upload your full design. Upload the part as you hope to receive it. And what we can do is work through a strategy. We could even often split and bond on our side and develop the strategy, so you may not need
Mhm.
to do that. And sometimes that's better for us to have that control because we may be putting in offsets and other things that we know is going to perform well for that process that you may not have that tribal knowledge about. So
Mhm.
always upload what you want, and this goes back to that previous question about shrinkage as well. Upload the design you expect to install. Don't try to offset those features or anything, and and then cross your fingers because we're actually going to be measuring to your CAD, for those features there. Um, what was I going to say? I had one more statement. So split and bond on that side, like one of the things I had to build one time was a really large round piece. And it just happened to be outside of the Fortis FDM platform. So Fortis goes 36 inches by 24 inches on the planar side, and it was beyond that. Instead of tilting up on the side, that may have affected my roundness by tilting up on the side. So actually the roundness was more secure by doing a split and bond. So sometimes just spinning the CAD will help us find the right solution because you're outside of the hypotheticals and you're into like real application. So uploading that CAD is super important. So you guys, we're at time. Thank you so much for the questions. We're always available to answer any more questions, and you can reach out. We're going to send an email follow-up with this recording in a couple of days from now. Please take a look at Additive Webinar 10 for a great discount on your next project. And again, thanks so much, Matt, for joining me today. And thank you all for attending.
Absolutely.
Really appreciate it.
Thanks, everybody.
Cheers, y'all. Thank you.